like what?
For example, like
Feet,
the length
pounds, inches.
the is like meter. I use maybe the wrote the answer in centimeter or something.
But if the answer value is correct, then this is okay. Yeah. All right. Okay, write this down.
Refraction. Can we get a prism?
I don't have any actually. I should actually buy one. I have a picture of one. I'll show you in this.
We use nails and the prism to.
No. We actually have something actually fancier than that. No, I know the way. The nails and the laser and the prism. Yeah, we don't do it that way. We have an actual nice machine for it. I'll show you it. Okay, you got this? Yes, you have this? Yes. Okay. There's quite a lot to do. Yeah. All right. So the lesson was called what did I say? Reflection, diffraction, refraction. Well, actually, what did I call it? Hang on, we'll get back to the start. Reflection, diffraction, refraction. Yeah. Please be careful with these words. So the first one is, what's reflection? Well, you might know reflection already from English. Reflection is when there's a change in the wave between two different media and the wave moves back to where it came from. So the most common example is when light hits a mirror. So what happens when light hits a mirror? It comes back to you, doesn't it? So I'll just draw that before you write it down. So for example, here is your mirror, and then here you are. Here we go. So the light hits the mirror and then it comes back to you. So this is called reflection, of course. And there's a picture. So that's reflection. So please write this down. Yeah? Next definition. So what's after reflection? What do I do next? Do I do diffraction next? I do. Okay, so diffraction is when the wave bends around small obstacles or when it spreads out when it passes through small openings. So if you look at this picture here, this shows it. So when the wave passes through this gap, you see how it spreads out? You see that? And if the gap is smaller, the wave spreads out more. This is called diffraction.
Switching it on or
Off. Okay?
what's the minimum temperature that's fine for you?
Hmm?
What's the minimum temperature fine for you?
For what?
What's the minimum temperature
For what?
for like weather?
-3. Hmm? Okay, can I go on? Who am I waiting for? Ah, as normal. Yes? I'm going on. Oh, I don't think. It shouldn't take too long, Grace. It's only one sentence. Oh, the picture of good. Okay. Right. What are they doing there? Yeah, but for what? Where? In the car park?
The motorway.
On the road? I might want to close the window then. No, you can sit down. Don't worry. Hacken has it under control. All right.
Sounds good.
The last one is refraction, and this is when the direction changes. So I'll show you the picture here. What happens is the light goes from air to glass, and then from glass to air. Each time it passes from air to glass or glass to air, the direction changes. So here the angle is, 45 degrees here, but it's not anymore. It changes every time it moves from one to the other. This is called refraction. Got this? Yeah. Okay. So that's reflection, diffraction, refraction.
What was the bigger two? The first and the third one.
Reflection, refraction. Think about the word, you know the word fraction. So in the first one, it's reflection, and in the third one, it's refract. Yeah, refraction. You try. What's the first one? Reflection.
Reflection.
And then, yeah, actually, I think it's probably good if we pronounce it. So in the first one, it is reflection, and in the other one, it is refraction. So it's for this one, you want to pronounce it like this, and the same here. You want to put the stress on the middle part because that's the difference. So you have reflection and refraction. You try, Amanda. What's the first one here?
Reflection.
Yeah.
Refraction.
Yeah, good. Grace, give it a try. Louder, can't hear you.
Reflection. Refraction.
Good. Sophie?
Reflection. Refraction.
Good, okay. I don't think you need to. Tacken, maybe?
Reflection, refraction.
Good, okay. And Jenny, I don't think you need to. Okay. Good, good. Any other questions about that? No? Yeah, don't mix them up, okay? Don't mix them up. Alright. So, some material, you don't need to write this just yet. Some materials allow light to pass through it more freely than others, whereas some materials will slow the light down. For example, did you know that light moves slower in glass than air? So, like if you had some like water, for example. Okay, so do you remember the speed of light? It's 3 multiplied 10 power 8. Now that's when the light is moving in space. But if the light was moving in water, it actually goes slower. Okay, and if the light moves in glass, it goes slower also. So that 3 multiplied 10 power 8, that's if the light is in space. But if it's moving in water or glass, it moves slower. Yeah? So we need a way to measure how fast the light can move. And we call that the refractive index. And the formula is quite simple. It's the speed of light divided by the speed of the light in the material, like the glass or the water. So please write this definition down of refractive index. Yeah, you got that? Okay, so let me just fix something here. You have this, yeah? Okay. waiting. There you go. I realise I have some wrong number here for the next part. Okay, let's go on. Right. One moment. Calculating. Ah, no, this laptop is great. It's perfect.
On the Black Friday, there's a big sale on laptops. Buy a new one.
I already have a new laptop.
Buy one for the classes.
Yes, but if
Do you
don't
think
have-
I'm made of money?
It's 100 something.
That's 100 and something more than what I have. Alright, okay, let's have a look now. Continuing. Where are we? Here. Okay. Right, so, notice that n must be between 1 and infinity. So, n is 1 in a vacuum. That's when the v and the c are equal in empty space. But usually the v is small, well, sorry, always the v is smaller than c. So if v is smaller than c, this will be more than 1. For example, if this value was half of this value, then the answer would be 2. And n equals infinity means the light has stopped moving, which we definitely don't want to look at those examples. So we just deal with n between 1 and infinity. So remember, phi equals c in empty space. So I think it's enough maybe just to make note of this. It should be between 1 and infinity. Can I go on? Yes, Amanda?
Okay.
It's okay? You sure?
Yeah.
Yeah? Alright. So now we're going to have a look at our first formula for this lesson. It's called Snell's law. And Snell's law is for refraction. And it's a way to calculate the angles. And the formula is this. Yeah, we can say I and R or theta 1, theta 2. So sine theta 1 over sine theta 2 equals n2 over n1. Where n1 is for the first material, n2 is for the second material. Theta 1 is the angle for the first material, and theta 2 is the angle for the second material. And here's the diagram. So, for example, this could be air and this could be water. This is the first angle, this is the second angle. And this is how we can calculate the angles. This picture is useful as well. N1 is the refractive index here. N1 is from this formula. So N1 is for, let me show you, oops, this material, the air, and for example here N2 could be for the water. Material 1 and N2 is material 2, yeah. I'll just draw it over here for you. For example, maybe this here is glass, and maybe this here, I don't know, is water. So the light comes in, at one angle. I'll call this theta 1, and then it moves at a different angle. I'll call this theta 2. So N1 is for glass and N2 is for water, for example. Yep. Okay, so write this law down. Snell's law. And yes, that is correct. It is 1, 2, and 2, 1. Write this down. And you should draw the diagram also. Yep. Here's a question. Where do you think the light is faster? In the air with V1 or in the water with V2? Which do you think is better, V1 or V2? V1. Because the air is closer to being like empty space than the water is. Yeah? In fact, air is nearly empty space. I mean, it almost practically is. Okay. Can we go on? Yes? Or you need more time, Amanda, Sophie? And Yemi? Okay.
Maybe you can get a break now.
Really? Nah.
No, after 15 minutes you need to maximum.
Nah, you're doing fine.
We have to study on this.
Huh?
In the EAP.
What's up with EP? No, we'll keep going and just finish early. It'd be better. Can I go on? Yep. Okay. So, in fact, sometimes it's possible to make the theta 1 so that theta 2 is 90. So I'll draw what that means. So for example, let's draw this now. So here is water, and here is air. And then here in red can be my laser light. Okay. And then this here is theta 1. So here comes my light. And it's possible to make theta 1 so that the light doesn't leave the water. In fact, the light moves across the top of the water.
Yeah.
And this here is called the critical angle. And it's the angle that makes this theta 2 90 degrees. So we call this angle C for critical. Yeah, you get the idea? And what's very interesting is, well, I'll wait till you draw this actually. So please draw this. Yeah. Yeah. Now what's even more interesting, I think, is that if you make the angle bigger than this, for example over here, a bigger angle, then the light actually comes back into the water. And we will do this in the experiment next semester, that the light actually doesn't leave, it comes back in. This is called, when this happens, total internal refraction. So we have here, I've typed it up. We can make the angle so that theta 2 is 90. This is called the critical angle. Let's see if we can get a formula for the critical angle. Let's see if we can calculate it. Can I go down? Yep. Alright, so we want an angle here, we'll call it C, that makes, let me use a different color. We want a C that makes a 90 here. So theta 1 equals C, theta 2 equals 90, N1 is N1 and N2 is N2. So Snell's law, sine theta 1 over sine theta 2 equals N2 over N1. Sine C over sine 90 equals N2 over N1. What's sine 90?
1.
Is 1. So you get sine C equals N2 over N1. So what does C equal? Sine inverse N2 over N1. But there's a very big but here. But N2 must be smaller than N1. Or another way of saying that is N1 must be bigger than N2. And the reason for this is because, whoops, this number here must be between 0 and 1. Because you cannot do sine inverse 2. It's maths error. So because this must be between 0 and 1, it means you must have N1 bigger than N2. So for example, if you have air, which is like N equals 1.0001, and if you have water, which N equals 1.3, you can only do this if you put this one first and this one second. The N1 must be bigger than N2. So you can calculate the critical angle for water to air, but you can't do air to water. So in other words, you can only have the critical angle if N1 is bigger than N2. So we can only calculate C if N1 is bigger than N2. If N1 is smaller than N2, then that means there is no critical angle. Sometimes you're asked to calculate the critical angle in the exam, so this formula is useful to remember. Yeah? You got this?
So this is the formula that we use to calculate the critical angle.
Mm-hmm. Okay? Do you have this? Amanda? Yes?
We have some.
Okay. Yeah? Yeah? Okay. So we've got the formula and we know the condition. The condition is n1 must be bigger than n2. If your angle is bigger than c, then the theta 2 is bigger than 90, and so the light wave will return to the first medium and never enter the second medium. This is called total internal refraction. You don't need to write this down, you just wrote it down earlier, when the light comes back. Yeah, so that's a critical angle. Now, next. You don't have to write this down either, just try to remember it. Do you remember in the last lesson we had all the different colours, red, orange, yellow, green, blue? Where was white? No? No? Did we have white? No, we didn't have white. You had red, orange, yellow, green, blue, but there's no white. Remember that? There was no white. So, in the last lesson you did not see white. Does anybody know why? No colour white. Yeah. In fact, there's no frequency for white because white is when you mix all the colours together. So if you have red, orange, yellow, green, blue, and you put all of these colours together, it makes white light. Yeah, you could even try it, yeah. So white light is a mixture of all the colours. That is, white is when you mix red, orange, and so on together. The result is white. So I just need you to remember this, that white light, like from the sun, or from a light or whatever, it's a mixture of all the colours. Now, you can just even write that down. White light is a mixture of all the colours together. Yep. Yeah. Now there's only really one place you can get white light. And the only place you can really get white light is from the sun. This light here, this is not really white light. It does mix all the colours together, but you can probably feel that there's more yellow in it than other colours. Yeah, like the light coming off of this, it kind of has a little bit of a yellow colour to it. There's more, I think there's more yellow in it than other colours. The only place you can get pure white light is from the sun. These are not really white, they're more yellowy white. Yeah? In fact, it's very, very, very difficult to make white light. It's very expensive. So these are not really white light.
Either off-white something, right?
Yeah, off-white, yellowy white, something like this.
Egg white.
Huh?
Egg white.
Egg white, yeah. Okay. In fact, there are other ways to state Snell's law. So one way we said was sine theta 1 over sine theta 2 equals n2 over n1. But in fact, that's only one way to state it. In total, there are 3 ways to state it. In one way to state it is by this formula, lambda 1 over lambda 2. Now, look. Oh, Grace, are you on your phone?
Yes. Sorry.
Pass it up, pass it up, pass it up. No, go on, give me Fahad, hand it this way. Thank you, thank you. Alright, now maybe you listen. Yeah. The white light, remember, is made of different colours. Different colours have different wavelengths. So when the red light comes in, it has one angle. But the yellow and the green lights, they have different angles because they have different wavelengths. So this is why the prism breaks the white light into different colours. Because there's different wavelengths. Different wavelengths mean different angles. Okay? So this is what's happening here. In fact, there are other ways to state Snell's law. You can state it like this, or like this, or in fact, that's not 1, 1. That should be 1, 2, of course, not 1, 1. Let me fix that. 1, 2. Yeah, so that last one here, come on, that's 1, 2. So these are the 3 ways you can state Snell's law.
Yeah, same way.
Huh? They all work, I mean, they all get the same answer. It depends, Yemi, it depends on what they give you in the question, what information you know. Usually it's the first one. Usually. Yeah, usually. Not always, most of the time. You know, like I'd say 90% of the time. Did you write these 3 down? Yeah. Okay. So, what the heck? Open it again. So you need to be very careful with your 1s and your 2s. So if you remember, in the first one, it's 1, 2, 2, 1. Come on, down we go. Here. Yeah, in the first one, it's 1, 2, 2, 1. But in the second one, it's 1, 2, 1, 2, and in the last one, it's 1, 2, 1, 2. So just be careful about that, okay? Please take care with the 1s and the 2s. Yep, you have that? Okay. Next. One use of Snell's law is in a lens. When light enters a glass, it will refract, but the lens is curved. This will result in different values of the angles. The lens is made carefully so that the refraction will cause the light to converge. You don't need to write this, but you do need to draw this. So what's happening here is the light comes in at theta 1 and theta 2. Theta 1 and theta 1. But the theta 2s are different here and here. Well, I mean, they're made so that the light will meet later. Maybe I can draw this. So what's happening here, if I try and draw this. So firstly, the light comes in. So, I can draw that better. The light comes in. And this here is the normal, because it's perpendicular. So this is theta 1. And then away it goes. And this is theta 2. And then likewise the light comes in here. And again, here is theta 1. I kind of drew this badly. Ugly. No, sorry, this way. Yeah, here we go. And then here is, there is theta 2. That's my x and y. That's my x and y. So what's happening here is, because the lens is curved, it's bent, the theta 2s will be such that the light is made to meet later. Whoops. So what you can do is you can make two rays meet as one here. And you can calculate this using Snell's law. Yep. So that's what I was trying to show you in this picture here. I don't know which you want to draw.
The diagram.
This one? M-E-E-T. Meet. Okay, can I go back? Yes? Problem? I know your problem. No phone.
No,
What's your second problem?
I don't forget about umbrella.
That's also a problem. Any other problems? Two problems. That's okay. Can I go back?
Yeah.
Yep. Right. So I'll do this question. So write this down, please. There's only one question to do, so we'll do this one. So write this down, please.
So you always give the speed in the material.
Oh, they could just simply give you the refractive index. Did you write this question down? Did you write all the words down?
No.
Show me what you wrote. Oh, come on, Fahad, you can write a bit more than that now.
When you do the part, I can write the part.
If you want to paraphrase it, that's fine, but there's not enough there. There's only one example to do, because there's only one formula from today.
Only one homework?
Well, two formulas. Only what?
Only one homework?
Oh, of course not. You know that. I do.
You're too young.
You know how it works.
Too young to see.
Too young and too simple.
Sean from the glass message.
Sean, yeah. Past tense for shine. It's irregular verb. So what is it? Shine, Sean, Sean. Yeah. Okay. Can we do this one now? You have it written down?
And the law.
Yeah. Can I do it? Yep. Okay. So the first part, part A, they want you to calculate the N refractive index for glass. So that equals C over the speed of the light in glass. So that will be 3 times 10 to the 8 over 2 times 10 to the 8. So for this glass, it will be 1.5. That's okay?
What's the unit?
No units. Unit free. No units. Okay, can I go on? Yeah? Okay, so B part. What you have now is you have your glass. And you have some air here. And your light comes in. And it hits the glass and changes its angle. So let me draw this line here. This line here is called the normal. So it comes in at angle, what angle did I say in the question? 20. And it leaves at some other angle, we don't know what. I'll call this angle here x. Oops. And we want to calculate x. You have the idea? Yeah. So Snell's law is sine theta 1 over sine theta 2 equals n2 over n1. So here n1 equals 1 and n2 equals 1.5. So you have sine 20 over sine x equals 1.5 over 1. So that means sine x equals sine 20 over 1.5. Can someone tell me what sine 20 over 1.5 is? 0. Oh, actually, sorry, forgot I have my calculator here.
0.23.
What is it? 0.228.
And the sine inverse.
Yeah, 0.228.
13.18.
Yeah, so therefore x equals, yeah, sine inverse this 13.18. So 13.2 degrees. That's the answer there for B, part B.
Now see.
Can I go to part C now? Do you have this? Yeah? So part C. So now what you have is you have your glass again, and you have your air here, and n equals 1 and n equals 1.5, and here's your normal. But this time the light is going from the glass to the air, but it doesn't leave. This angle here is C, and this angle here is 90. So we saw the formula earlier. It's sine inverse 1 over 1.5. So C equals 41.8 degrees. This is the critical angle. Yeah. Yeah. Okay. Oh, so actually the answer is theta 1 should be bigger than 41.8, and then what will happen is the light then will come back in if it's a bigger angle than this. So this is the answer here. I suppose you could say equals. Okay.
That's the references.
For my pictures, just. I don't make these pictures. I haven't got that much time. Alright, so these are the questions. They're not long questions. You know, they're quite short to do. They're not too long. Why are we packing up? There's still time. Dude, there's still 10 minutes left. So I want you to do these for 10 minutes. Then you can go.
I don't have page message. Search case. See?
Well, do it on that.
See?
No.
The board?
Yes. For 10 minutes. That's all I ask.